Funding for this program is provided by Annenberg Lerner.
Hello, I'm Pardees Sabetti, and this is Against All Odds, where we make statistics count. Today we have a challenge. See if you can guess how much money is in this vase. It's a pretty random mix of quarters, dimes, nickels, and pennies. And to give you a hint, I'm pouring the last $10 in now. Jot down your guess, and at the end of the segment, we'll let you know how well you did. No prizes, I'm afraid.
As long as we get to 250 or so, we should be fine.
But there is a prize,
Right,
the vase and its contents, for whichever student taking our challenge at Endicott College in Massachusetts gets closest to the right answer.
What we're trying to demonstrate is something called the wisdom of the crowds, which is that the average of all of the guesses will be probably more accurate than most of the individual guesses. The reason is that everybody has some experience about how much money that might be, and some are going to guess too high, some are going to guess too low. It'll kind of all average out, we hope, to show that the average will be better than most of the individual guesses.
Now, John Kelly, a professor at Endicott, and his student Sarah Lovell aren't being totally upfront about the purpose of the experiment. A little harmless deceit is common in psychology, where knowing the real aim of an experiment would negate it. Sure, John and Sarah are interested to see if the wisdom of the crowd holds up, but to get at the real goal of the study, we need to take a closer look at the clipboards the students are holding. The clipboards are the type with storage compartments for extra paper. One of them will have just a sheet or two in the back for the duration of the experiment. It weighs just over a pound.
Got just about 1.1 pounds.
A second clipboard will always be half full of paper and weigh just over 2 pounds, while the third is full of paper and weighs just over 3 pounds. Each student only ever gets to hold one of the clipboards, so they are unaware of the weight difference. And so that the students aren't tempted to rest their clipboards, especially the heavier ones, on the table.
The only thing we ask you to do is not to touch the table because it is unstable and it could tip over. Okay? The theory is that the differently weighted clipboards will unconsciously bias them to give different estimates, so that the people with the heavier clipboards will give a higher estimate, and then those with a lighter clipboard will give a lower estimate.
$75.50. Oh gosh, I was off. I guess 380. I don't know.
Well, nobody knows how much.
29 cents.
Might be one of them might be right. Who knows?
John Kelly based his experiment on a published study in which people holding differently weighted clipboards did estimate quantities differently. Studies like this have become popular in experimental psychology. The idea they are testing is that physical experience can influence our thinking in ways we are unaware of. So for instance, one study showed holding a cup of warm coffee as opposed to a cold one made people perceive others as warmer, more generous, more caring. And it gets weirder. Another study showed putting together a simple puzzle made of pieces covered in sandpaper as opposed to ones with smooth pieces caused subjects to make harsher judgments about others. Yet another study had people handling a hard object like a Rubik's Cube or a soft one like a piece of blanket. The hard object made subjects more likely to judge others as rigid and inflexible than did handling the blanket. So let's check in with John and Sarah's study. Over the course of a couple mornings, they gave well over 200 students a chance to win the money. A third holding the lightest clipboard, a third the medium weight one, and a third the heaviest. Estimates varied wildly.
$45, $75.63.
$95.07.
I said $112.
I guess $63.75.
I guess $72.50.
$19.55.
$99.
$99?
$777.77.
$178
And 20 cents.
and 20 cents.
I guess $529.61.
I guess $86.70.
The range of choices or guesses that people make is enormous, from very little as $10 to as much as $1,500. So you have gigantic amounts of variance, and if our effect is relatively small, as compared to that error variance, it's going to be very hard to detect.
529.
John and Sarah entered the guesses, grouped according to the weights of the 3 clipboards, then computed the average guess in each of the 3 groups.
If you just look at the means, it's very promising. We've got, for the light clipboard, $107. You look at the medium level clipboard, it's around $130. If you look at the heavy clipboard, it's $143. So we have a very nice linear effect, exactly what we predicted. If you plot that with a graph, what I can do right like this, you see, this very nice, beautiful linear effect, and you think, hallelujah, we got it. However, if you then do a box plot, you look at the actual distributions, you see there are extreme outliers. By chance, probably, in groups 2 and 3, there's more outliers than in group 1. So it's possible that this linear effect is driven by just a few people and might just be a fluke.
The most striking thing about John's data is the extreme variance within each group, as compared to the variance between the means of each of the groups. In other words, the noise is threatening to swamp out any signal that might be there. To see if there is a meaningful signal, if in fact the variance between the population mean of the 3 groups is significantly different, he turned to a technique called a one-way analysis of variance, or ANOVA. In asking the question, is there a significant difference between the population means of 3 or more groups, a one-way ANOVA actually sets up a hypothesis that there is in fact no significant difference, the so-called null hypothesis, where the population means of the 3 groups are really the same.
It's kind of a weird thing that we test the null. You'd wonder, why don't we test the actual hypothesis? The reason is that the hypothesis is non-specific. We have a vague hypothesis that heavier clipboards should result in higher estimations, but we don't have any idea really about how big that effect is, so it's very hard to generate probabilities when you have this kind of squishy kind of hypothesis. The null hypothesis is that all of the means in the population are the same. So in other words, if we did this infinitely, that the averages in the 3 groups would really be the same, that there's absolutely no effect of the weight on people's estimations.
Of course, what John is hoping for is sufficient evidence to reject the null hypothesis. To do that, he runs an ANOVA using software to compute a statistic called F. The numerator measures how much variability there is between the sample means, while the denominator measures how much variability there is within the individual observations. In John's case, F equals 0.796. To reject the null hypothesis, the probability of obtaining a value at least as extreme as F equals 0.796 needs to be less than 5%. In other words, a p-value less than 0.05, the usual statistical standard. But the actual p-value John finds is 0.45.
So in this case, since our p-value is 0.45, there's a 45% chance of getting this big a difference, or bigger, just by chance. So at this point, we cannot say that we have, by any means, shown that this hypothesis is true.
One of the underlying assumptions of ANOVA is that the data in each group are normally distributed, which is not the case here given the skewed nature of the data. John's students tried some statistical manipulations on the data to make it more normal, and then reran the ANOVA. However, the conclusion remained the same: no evidence that the means of the 3 groups are different. But what if the data had looked like this instead? The sample means are the same: $107, $130, and $143. But this time, the data are less spread out about those means. In this case, the value of F turns out to be 33.316, and the corresponding p-value is essentially 0. Our conclusion in this hypothetical case would be to reject the null hypothesis. The population means do differ. And at that point, we could turn to different statistical tools to explore the differences further.
$45.
But sadly, in John Kelly's study, The harsh reality of a rigorous statistical analysis has shot down the idea that holding something heavy causes you, unconsciously, to make larger estimates, at least in this particular study.
Inevitably, you have to be disappointed because you put a lot of work into it and you find it didn't work. And there's actually reasonably good evidence that a lot of studies are wrong, that it's going to happen. A reason for that would be, imagine if this was me and I was continuing to do this kind of work and I was the first one to do it. I'm not, but if I was the first one to do this particular kind of study, I might keep working at it and try this and try that and try another thing, and eventually I might get it to work. Now, that might mean it does work under those conditions, or it might mean I just got lucky eventually.
But if the real experiment didn't work, what about the cover story that John and Sarah were testing? The idea of the wisdom of the crowd. The actual amount in the vase is $237.52. Here's a histogram of all the guesses. You can see instantly that most people were way too low, almost half of them being under $100. The mean of the estimates is $129.22, more than $100 off, but still better than about 3/4 of the individual guesses. So the crowd was wiser than the people in it, but still not all that wise. Unlike the actual winner, Chris Johnson, who turned out to be an accounting major who has worked in a bank.
Congratulations. Thank you.
His estimate was $235.
You were within $2.52, which means so we are going to give you this coin jar. So literally. So here you go. It's really heavy.
Thank you.
You got it?
Yeah.
That's for you to keep. And I guess you go to your bank and do some more counting, essentially.
So how well did you do? We borrowed back the vase for this taping and to give you one last chance to compare your guess with the reality of $237.52. Now the jar and coins are on their way back to our winner. I'm Purdy Sabetti for Against All Odds. See you next time.
Funding for this program is provided by Annenberg Lerner. For information about this and other Annenberg Lerner programs, call 1-800-LEARNER and visit us at www.lerner.org.